Okay, 2 students in class, one missing at the moment. Okay, right. Now, yesterday we talked about stress. Stress, we have 2 types of stress. One is surface force, and another one is body force. So before we know about stress, because stress comes from force. So we have 2 types of force acting on fluid. Fluid, we have 2 types of force, surface force and body force. Okay, and surface force give you stress, body force give you a gravitational effect, which is give you this formula, rho g dv. So later on we'll explain more about this equation. And last lecture we explained that when we have a small forces acting on a small area, delta A, this force acting at a certain angle is a vector that we can expand it to normal direction and tangential direction or tangent direction. Okay, so these are the basics that you learn in your previous module. You learn about vector. So this is the application of vector where your force now expand to normal and tangential. Okay. Now this force, if you divide it by area, it will become stress, because stress equal to force divided by area. Okay, and why we know that it is a normal stress, because the force direction is perpendicular 90 degree to the area. Okay, when the force is parallel to the area, it becomes shear stress. Shear stress. And shear stress is important for fluid because fluid only acting on shear stress. Okay. And we have 2 equations yesterday or in your previous class. Shear stress equal to force in the tangential direction, F divided by A, and normal stress, you take the normal force divided by area. So you're going to look into these 2 equations many times in later chapter. So again, these 2 is a very important equation for this module. Okay, so yesterday we stopped at here. Now we move forward. This is under your tutorial question number 15, 1-5. So you see these 2 diagrams. Okay, now how to read this diagram? You start with the axis, because when you deal with force, you deal with stress, you need to know where is the orientation of your axis. So you have X, Y, and Z axis. And you have a plane here, 2D plane. And point number C is in the middle of the plane. So all the force towards X direction, we write Fx. And again, you see this small letter symbol, del. It means it's a small changes of fluid, small changes of the parameter that next to it. Okay, because we assume that this is a very, very small element. So the force that can act on this small element is very small. So that's why you use the delta symbol. And same with others direction also. So if it's going to Y, then we write del Fy. If you go to Z direction, we write del Fz. On the left diagram, referring to the force component. So we're going to convert the original force presentation to stress component. Force we convert to stress. So just to recap what we learned in our previous lecture. What is the definition of stress? Stress, we take force divided by area. And again, when we talk about stress, our force direction is always 90 degree to our area. Okay, or it's a normal force. It's a normal force. And we talk about shear. Shear also is a stress. Shear stress also we take force divided by area. However, our force will be parallel to the area, which is the tangential component. Okay, so Ft is here. Okay, and the T is referring to the area that this force acting on. So by looking at the diagram on your screen here, we look at the Fx component. So Fx component is 90 degree to the area here. So it becomes stress. Okay, it becomes stress. Okay, because stress equal to F divided by area. So this is a small area, so we take this component divided by this area, we get stress. So again, the notation for symbol, if you see this one is stress, the first number is plane. The first number is plane. Second number, okay, right here, maybe on your side note, this is a plane. This is direction. What mean by plane? Let's say I draw on this diagram. If you're having a 2D, so this plane is x plane on an x plane, meaning this plane, 2D plane here, cut through the x axis here. Okay, so we have plane 1, plane 2, or on the x-axis. Okay, so when you're referring to x plane, then you use a symbol of sigma or stress x. The first notation, the first notation is referring to the plane. Second one referring to the direction. For example, this direction is to the x direction. That's why we have x here. Okay. Apply for other two also. The notation, the subnotation. So later I'll explain about the shear. We go to the subnotation first. So why you are seeing xy here? It is because this stress is on the x plane and going to y direction. That's why we write xy. And this one also. Why is xz or xz? Is because this force is on the x plane to z direction. That's why something, I just put a general symbol, something xx, if I write a yy will be the different, a zz will be different. If I write a xy will be different from a yx. You're not same, huh? So I will test you later on this understanding on subnotation here. Okay, again, the first number is plane, referring to the plane. Second one is on the direction. Okay, right. Then we have cleared the stress just now. Now what about this one? Why this one becomes shear? Because if you look at y on the left hand side here, Fy is going parallel to the area here. So again, if you have a parallel, you'll become shear stress. And why this is x, this is y, because it's on the x plane in y direction. And also the force of Fz here, why Fz becomes shear? Because the component of Fz is parallel to the area here. That's why force here become shear stress. And why this one become xz? Because this force is on the x plane in z direction. Okay, I'm clear on the notation. Any question on this slide? Any question on the notation? Any one of you still not very clear? Why this one become xx? Why become this one become xy? Why this one become xz? Let me check attendance. Who still not here? Okay. Who missing?
Still a little bit confused about
On which one?
So we have one normal stress and another one shear another shear stress, yeah?
Correct. So which one you are not sure, not clear?
The position of the plane, it's in the x plane, right?
Okay. Let me draw on the empty slides. Okay. Now we know that we have three axes.
Yeah.
X, Y, Z, and Y. So if you talk about x-axis, so let's say I talk about, or someone talk about, if a particle moving on x plane, what does this statement mean? It means that if you're looking on x-axis only, there will be a plane. This plane is this plane is maybe I draw a direction here so that you can see. This plane consists of Z and Y. It's a 2D plane like a paper, cut through x-axis, and it's a 90-degree angle to the.
So this plane just has like a point in x.
It's just like a paper, like a sheet of 2D paper. Yeah, it's not a point. It's a 2D, like a 2D paper.
Yeah,
like a piece of paper. Yeah.
Going in Z and Y.
Yeah, in the Z and Y orientation.
So that means Z and Y axis is proportional to it. Yeah. Not
So
parallel.
if you want to draw, you can follow the Z and Y plane.
Okay.
Then you draw a plane like that.
Okay. So
this is called X plane.
Okay.
X plane at Z at x equals 0 at this point.
Oh yeah. So that means x is perpendicular to the plane.
Yeah, it is actually following Z, Y and Z axis.
Yeah. That means So for the x we have normal stress, and for y and z we have shear stress.
Yeah, it means that you imagine you are holding a paper, just following the orientation. You follow the Y and Z orientation.
Yeah.
But you are moving on the x scale.
Okay.
So you try to imagine. So because maybe when you learn about XY plane, maybe someone do not explain that to you, so you might confuse.
Oh yeah. No, it's okay.
Yeah. So when we talk about X plane, means something like this. So just to further clarify, so what happens if I change it to Y plane? When we talk about Y plane, so I think by having the same understanding, let's us use the same axis again. What happens if somebody talking about Y plane? So Y plane is focusing on Y axis, Y direction, but you will take the form of Z and X orientation, I can say. So it will follow like that. So this is called y plane.
Okay.
And this y plane can move to the location following the y scale here.
Yeah.
Okay. Yeah. So further, if someone talk about z plane, it will be the same.
Yeah. That's okay.
Yeah. So I think I better explain this one so that all of you clear. Because this orientation is important when you learn about physics or engineering things. Okay, so if someone talk about z plane, so z plane means focus on the z axis, and the plane that you're drawing is actually take the form of like this. So,
Yeah.
okay.
Okay.
And then this plane moving in a scale of z. All right. Another one. Oliver, you understand, right? On the plane and all this?
Yes, sir.
Okay,
Explain
good.
after you understood.
Yep. Okay, so now again, a reminder for notation. The first one is about plane. The second one is about direction. So be careful on notation when you write your answer in test later on, yeah? Okay, now, this is just a derivation or explaining what we have, we already learned. So when you write stress x means stress on the x plane, x direction, given you by you taking the force in x direction divided by A. Same with shear stress at x plane in y direction will be equal to you take the force that parallel to the affected area, the force that go parallel in the y direction. So you take Fy divided by Ax. Okay. And the same with shear stress Xz here. Okay. You take the force that going to Z direction. Why we focus on Z? Because our shear stress we denote as Xz. We're looking at X plane, Z direction. So we're looking at any force that going to Z direction. So we take Z direction, and then as long as it's parallel to the area, it becomes shear stress. Okay, this is only one side, and we talk about 3D, we will have three sides. So this diagram you can find in your tutorial handout, question number 16. It just asks you a simple question: are you able to explain the notation for the stress and stress in the diagram below? So maybe the question can extend to another one called do you know the notation for the shear stress below? So again, so just now we talked about this plane. The example is talk about this plane. I just pick one more, and then the rest I think you can go and look at it later on at your free time. So maybe I look at this one, the top one, the one on your screen here. Okay, so why we have a shear stress in y direction like that? Because on this area, we assume, because this diagram extract from a cube that having force in all the direction in 6 faces, and the force is acting outwards of the body. Okay, imagine you have 6 forces, 6 faces. Each face have force acting outward. So each one of it will give you value of shear stress and normal stress. Okay, so this is a normal stress. This is a shear stress. Okay, normal by this symbol, shear stress by this symbol. And if you look at the positive direction, it's always follow the axis direction. Okay, yeah. And if you look at the left-hand side of the cube, you see the direction is a little bit different. Okay, a little bit different from the right-hand side. It's the opposite direction of your right-hand side diagram. So right-hand side diagram is what we developed just now. You look at the left-hand side of the diagram, you see that the direction of the normal stress here, stress xx, this one also moving in the x-plane, x direction. However, the arrow is pointing to the left. Why? Because we assume the cube is in balance. So we need to balance all the force that we see on the body. Okay, so on the right hand side, if your arrow is going to the right, there must be a force to balance it. So you will have sigma xx to the left. And you look at the left hand side, why this shear xz is going opposite of the z direction? Is because also it's going to counter the shear stress at the right hand side. Because the right hand side is going along z-axis. So to balance this shear stress, this stress have to go against the z-axis. Then same with the sigma or your shear stress xy. Shear stress xy again in x-plane y direction, and the direction is opposite to the right hand side to balance the cube. So if the direction is not balanced, then the cube will rotate and experience deformation. So it will be the same for the other plane also. So this one will take some time to study. Important here is that you know how to read the notation, right? So when the question asks you to find y. Interesting. Okay, another question that maybe can test you. All right, now let's test you. Okay, maybe back to the simple diagram like this. What is the value of shear stress xx? What's the value if you're referring to these slides? What do you think, and why? Why you give such an answer? I'll give you like 1 minute to think about it. What is the value of shear xx in this case?
What do you mean, sir, by the value? By the value?
Meaning, if you look at this diagram,
Okay.
How do you find shear xx? What is x plane? X direction.
Yeah.
So you look at this one. So what's the value, or is there any value for shear xx here? Any force that create this component, shear xx, in this case, in these slides?
No.
There's no. Answer is 0.
There's none.
Yeah, answer is 0. So sometimes there's a bonus mark in the question. Just try to trick you or try to ask or test your understanding. So maybe suddenly a question will try to ask you something that just to test your logic thinking. like for example, this one, the slides, I just, after you solve all the question, then
Okay.
certainly there's one particular section, just maybe give you 3 marks, free 3 marks, or 3 marks, 4 free marks for you. I just simply ask you by based on the diagram, what is the value of, for example, this shear XX?
Okay.
What's the value? So determine the value of shear XX just for the bonus point, right? The value is 0, and then explain. Because on this graph, there's no force that acting in this direction. Okay, because there's only one force that acting in x plane in x direction, which is this one, and this direction give you stress and is not shear stress. Okay, it give you stress, give you stress or normal stress, and not shear stress. Okay, yeah. So yeah, again, how you know that there's no value? If you look at the first notation, if you see x, the first one is x, you look at all the force in x direction, and then you're referring to area that you're looking at. So if this force is perpendicular, meaning straight away you know there's no shear loading, there's no shear force on this area. You only have normal stress. Okay. So these are the simple logic that you can go through. Okay, we're done with the notation. This one will come into place when we try to solve more complex problems. Okay. Now we look at your tutorial question number 17. We try to understand how to define a deformation in a fluid, right? Deformation in a fluid. So again, we look at a diagram on the screen. We have two parallel plates here. And then there's a medium, or there's a something element inside between these two bars. And the distance between these two bars is delta y, change of y, delta y is change of y. And on this diagram, our reference is this position. Below is our bottom plate. You can call it as a reference plate because our axis start from bottom, this plate here. And then there's a x direction with this, we call it delta x, which is in the x direction, with the, you can say as a length of this element. So this element is having this one, and then the z direction, because this is a 2D diagram, so all the z direction we assume as 1. The value for z is 1. So yeah, so for this one, if you want to find the area of this MNOP, then you take del x times del y to find the area. Okay, right. So if the one on the left here, you will see is element at rest, then certainly there's a force applied on the upper plate here. We have a force acting on the upper plate, and the fluid element will deform, will slanted to a certain angle, alpha. Okay, again, don't intimidate it by the symbol. This is just mean that it's a small changes. Okay. So the element will deform at an angle of alpha, and this one, delta u, the u is displacement, right? Or not displacement. For this module, u is there's a velocity to the right, and there's a change of L from M to M dash here. Okay, so this here to here, there's a distance here. Velocity, this is velocity. And the velocity is constant. The word constant velocity is important in this module Because later on we will look at F equal ma, will be the second Newton law. And when you have a constant velocity, your acceleration will be 0. Okay, so this is just a add-on information that will help you in the next chapter. Okay, now we will try to define a shear stress again. Shear stress is the stress that created by the force that go parallel to the area. The area that we're looking at is here. And if you want to draw in 2D, it's the area and the force is parallel. Is delta F go parallel to the area here. So given by this equation, we take the force divided by area. So the direction is x, so we take the Fx divided by AY in y plane. Okay, AY means y plane. I already explained definition of plane. So if you see AY means on a y plane. Okay, so this is the axis x, y, and z. So again, you're looking at y plane here. Okay, y plane like that. Okay, right. So this one very straightforward. And when you remove the mathematic limit to small changes, then you can change the small del into d. This is a mathematic procedure. So if you remove the limit, then your equation you can write as d small difference in Fx divided by small difference by AY. So it's quite straightforward. Just need to remind you is on the notation yx. Okay, plane y, x direction. Plane y. This is on plane y, x direction. Okay. Any question on this slide? Anything that seems not clear to you, or you're quite, or something that doesn't make sense to you?
No, sir, it's clear.
Good.
Yeah, it's clear, sir.
Okay, good. Okay, let me check what happened to Ku. Okay, right, Ku's still not here, so we will check on him later. Okay, move a bit faster because we are a bit behind. And this diagram that you see on your tutorial, the diagram number C, is just after a certain time. So this is T delta 1 and this is a T2 delta, means you see that the fluid is able to continue to deform. This is a property of a fluid, and this one do not happen in solid. Solid body, it will break already, but fluid will continue to deform under shear stress. So this definition is in the slides also, and this one is in your tutorial question number 2. This is a definition of fluid, which is important when you study about fluid. Okay. Yeah. All right. The next one, we talk about shear rate. The third equation. I think this is the first equation that you learned today. We call it shear rate. Shear rate or deformation rate of the fluid, we focus on this angle alpha. Okay, so you see the word rate here means something changed with t, or in mathematics you will see something over dt. It's a rate. So if you combine the wording shear rate or deformation rate, and you know that shear rate is something to deal with alpha, so you write in mathematics, you write del alpha divided by del t with the limit. So you remove the limit to 0, you can write in a more formal way. Is called you can use the d alpha divided by dt. Okay, here this term is mathematical term that you're dealing with a very small changes down, right? So that's why you need to use the limitation to convert into d, right? So if the question asks you to find the shear rate, you don't need to write this one. You need to know straight away shear rate. You write shear rate equal, okay, shear rate equal. Of course, you write the full name. Shear rate equal to d alpha dt. You write like that, you get 1 free mark for the formula alone. So it's quite easy to score for this module. Huh? So as long as you know which is the correct formula to use, you write in the answer, you will get marks for that before you try to solve in more detail. Okay, and because the alpha is very hard to measure in a real case, so we only know that there's an angle happening, but in the real life, it's very hard to monitor. So we need to change this alpha to a measurable data, for example, the length here and the height here. This one we can measure. So when you want to convert the alpha in terms of L and also Y, for example, in this case, the only thing that link angle to all these parameters, you need to recall the trigonometry equation, the sine, tan, cos relationship. Okay. So the next step is we're trying to remove the alpha term and then put in the L or Y term. So we move our dl. How we find the change of length here? We make full use of the velocity. If you take velocity times the time, you're going to get length. Okay, velocity is in meter per second. Again, dimensional analysis. This one you'll see in chapter 5. Times 1 over times time s. Sorry, you'll get cancel the time. You'll get in meter form, meter unit. So this is how you find. So to find the length, we make full use of the velocity and the time. So we get this term. So the first procedure to remove the alpha, you try to extract data from the diagram. So you take velocity times time, you get the length. And then if you learn about trigonometry, you know that when you have tangent, for example, when you learn about tangent, trigonometry, so A, B, and C. So tangent alpha equal, this is alpha, this is tangent theta equal to A divided by B, correct? So, and so on. And when you learn about a pi or circle that give you R and S, R is the radius, S is the circumference. So S equal R theta when the theta is small. Okay, R is in radian. So if your theta is small, then you can use S equal to R theta. Okay, so that's why the second equation for length, we can take y or del y here, del y is from here to here, times the alpha to get the length of m to m comma. Okay, any questions so far? There are two ways to get the length. One is use velocity times the time. Another one, you use a trigonometry concept. And because we assume this alpha is very small, and this happened in real life, also very small. So by using this concept, R times the theta equal to S. This is a a cylindrical body. So you can take the y times the alpha, you get the length. Okay. Now you start to see what you learn in your trigonometry and apply here already. Okay. Then we rewrite in the term that we want. So you can adjust because these two is the same. First equation give you a del L also. Second equation give you del L also. So you put these two together. Then you rearrange in a term of del alpha over del t equal del u over del y. You rearrange this one, del u over del y equal del alpha del t. Okay, remove this term over here because these two are multiplication relationship. You pull something from its original position, you're going to change the operation. Multiplication, you move from left to right. When it arrives at right, it becomes division. Okay, and so on. Any question on the conversion on the this formula? Why suddenly we can get this one? Any question?
No.
No, sir.
Okay, good. So maybe I'll go a bit faster. So again, when we remove the limb for the small del, we can change the small del into d. d alpha divided by dt equal to du over dy. Then you compare this definition, this mathematical model to the definition of your shear rate. So your shear rate can be written in this form. Your shear rate, because your alpha is very hard to measure, your shear rate can define in velocity divided by the change of the height, y, okay, du over dy. This is your shear rate. Okay, first equation for today. Shear rate equal to du over dy. So it's important you understand why we can use du over dy to calculate the shear rate or deformation of fluid. It's original from the focus on alpha. Yeah. Okay, I think this one's straightforward. Move to next slides. So I just summarize what we learned. First, we learn about shear stress. Here we take the force parallel to the area. So and the direction is on the x on the y plane. So we have shear yx equal to fx divided by ay. And the shear rate or deformation of fluid, rate of deformation. So there's a word missing here. Is a rate of deformation or shear rate equal to du over dy. We try to find, or the next question we should ask ourselves, what is the relationship between these two? Right? They must be a mathematical model that help us to convert or relate shear stress and shear rate because it happened on the same body with its fluid. Same force, same velocity, and the deformation is the same. Okay, only the parameter we use to calculate is a bit different. So how do we link these two? How do we link shear stress and shear rate? Okay, now we need to start to learn about the new term called Newtonian fluid. Okay, the definition of Newtonian is that when you have a body that this one is proportional to the shear rate. Yeah, the definition of Newtonian is when the material behave in such a way where the shear stress at proportional to shear rate. When the material behave, these two means that if shear stress increase, shear rate increase. If you have this kind of behavior, then the material is a Newtonian fluid. Yeah, so this is the definition. Again, when it comes to test or exam, because it become an online test, we're going to ask you on the meaning of the value that you get. Okay, so if you able to find an equation that give you linear equation, if you put number of shear stress and number of shear rate on a graph, then it become, you can see the trend. If it's proportional, then it is a Newtonian fluid. Other definition, if these two do not agree or do not proportional, then it's a non-Newtonian fluid. Okay, so you based on Newtonian fluid definition, then you explain non-Newtonian. What mean by proportional? It means, let's say you plot shear stress versus shear rate, you'll get one line like that. Okay, one straight line like that. It means you have y equal to mx plus t relationship, which is a linear graph. So you have a linear or proportional to each other. If you have this kind of behavior, again, you are having Newtonian fluid. If you plot the graph, you get something like that. Okay, you get this kind of curve, or you get this kind of curve. Then this is a okay, that this graph is shear versus shear rate. Then this one become non-Newtonian medium or non-Newtonian fluid behavior. Okay, so by the end of this course, by looking at the experiment data or by processing a data that published by someone, if you see shear stress versus shear rate graph, you can straight away tell that this researcher, he is working on Newtonian fluid or non-Newtonian fluid by looking at the behavior of the graph. Yeah. Any question on Newtonian and non-Newtonian definition? Anything that you're not clear?
No, sir.
No, sir.
Okay, good. We move forward. So this is how we write lah. Okay, Newtonian. This is mathematical model. We write shear and proportional symbol to our shear rate. So we know that we can convert this proportional symbol in mathematics. We can convert this one in a constant value. You can put k, but we know that at the end you'll still see a viscosity symbol. So we straight away use a mu symbol to represent the constant relationship between your shear stress and your shear rate. Okay, this is a conversion of mathematics relationship. A proportional, you convert to a constant value. Okay, for example, you have y proportional to x. You can convert this one y equal to kx, or y equal to mx, or y equal to ax, or any alphabet you like. There's a constant value between between y and x in this case. Okay, so in this case, the constant value that in front the shear rate is called dynamic viscosity. Also, this one can be absolute viscosity, or we call it dynamic viscosity. We have two types of viscosity. Yeah? We have kinematic, just for info, kinematic viscosity and dynamic viscosity. Okay, so we have two types of viscosity here. So we'll look into it in detail. But in this case, when you have a shear stress and a shear rate, then this one fall under dynamic viscosity. So this is the, I think, the third equation you learn. First one, you learn about shear stress. Second one, deformation, a rate of deformation of fluid, or shear rate. These two, you combine these two, you get a new equation with a constant value. And again, this equation only works on Newtonian fluid. No? This equation developed based on the concept Newtonian fluid. Okay. Now we look at dimension. This is just a dimension analysis. So if you take shear equal to shear, we take force divided by area. So dimension is you take force divided by length square. Okay. And du over dy, what is u? Velocity. Velocity is speed. Speed, you take length divided by t. So we are looking at the dimension of length divided by time, and the y is length. So we try to, because previously we did mention in the equation everything must be balanced, meaning the dimension on the left must be equal to dimension on the right. So here there are some missing. We try to find what is the dimension of our constant value here, which is our mu, which is our dynamic viscosity. What is the dimension of this one? So we try to do mathematics here. It's just a simple mathematics. You look at the left, look at the y, and then try to find what is the dimension. What is the missing dimension here? Okay. So if you cancel out, your shear rate is only 1 over t, and the dimension for mu, you will get ft divided by L square. Okay, so by doing the balancing that I showed you just now, you will get your mu, or dynamic viscosity, in the unit. This is, we are talking about unit. Unit ft divided by L2. Okay. Do you need me explain on this one? You understand how we get this one? Yeah, go ahead.
No, no worries, sure, sir.
So okay, understand.
Yeah.
Okay. So what about if you try to write our mu in a mass dimension? Can you write? Because initially our analysis tells us that our mu or viscosity is in terms of force, time, and length square. Can we write in mass? Because mass is more useful when we have a realistic case to analysis. So we start with the Newton law, second Newton law. Again, second Newton law, F equal to ma. F equal to ma. M give you mass times acceleration. Acceleration is length divided by time square. So we can convert. If you see this term, if you pull this term inside here, okay, you'll get your mu is in terms of mass divided by LT. Okay, just a conversion of dimension. Okay. So on the left is Pascal dot second. How we know it's Pascal? Because force divided by area, we get Pascal, or Newton over meter square. Newton over meter square is Pascal. Or your mu will be in the unit of kilogram over meter dot second. So your viscosity, you have two units. So sometimes you need to convert the unit in Pascal. Sometimes you need to convert the unit in kilogram. Conversion on the value of mu you can find in Appendix A, and how to convert from Pascal to kilogram also inside Appendix. So if you look at Appendix that I ask you to download, you will see that in table Appendix A, you flip to table A8. You will see this table for water, for example. So you will see that the water change with the temperature, and there's a density, dynamic viscosity, kinematic viscosity, surface tension, vapor pressure, bulk modulus. So today we'll look at dynamic viscosity in the unit of Newton second over meter square. Actually is a Pascal second. Why Pascal second? Because Newton over meter square is Pascal. Okay. All right. Okay, we stop here for a while. We have maybe 10 minutes break. Okay, I stop the recording.